I would like to discuss those and show you what are sort of the relationships between them. So, chemical reaction networks. So, and actually, all of you have seen this already in the one of the exercises by Mark, which dealt with this exactly this setting. So, I consider a system of reversible reactions. So that looks like this. So I have coefficients alpha i's. So these are natural numbers, and then there's a bunch of chemical species which I denote by x. So x1 up to xd. So here's a sub d superscript r xd. So the r is just a superscript that denotes the number of the reactions. So I consider multiple reactions. And the reactions, they can occur in two directions, so both forward and backward. And on the right-hand side, you obtain a similar thing. Now I denote the coefficients by betas of x1 up to beta of species d xd. So this is a bunch of chemical reactions, and they are indexed by r, and we have capital R of them. And so you see that each of those reactions can occur both in the forward direction and the backward direction. And there's a reaction rate associated to those. So there's the forward rate, which I denote by k subscript forward of this reaction. And there's a backward rate in the other direction. So this is just sort of the chemical notation, and then there are two mathematical models which are commonly used, and I would like to describe both of those. So two mathematical models. So the first of those is a stochastic model, and it's discrete. I think I have something for you, Marek.
Oh yeah.
And the second model is deterministic and continuous. And I will show that there are gradient flows associated to both of these situations. So let me first describe the stochastic model. So part 1, stochastic model. So in the stochastic model, what you observe is the number of particles of each of those species. So the observable I denote by n, capital N. So this is a vector, and you're just counting the number of particles. So n1 up to nd of each of your d chemical species. So this is just a vector of integers. So ni is the number of particles of the species xi. Okay, and well, the usual model is that this number evolves according to a continuous time Markov chain. So n evolves in time. To a continuous time Markov chain. with the following rates. And now they're sort of, each of those reactions induce sort of two possible transitions. Namely, a reaction can occur in the forward direction or in the backward direction. So what can happen is that is the following. So the first thing is that, so you have like n particles, and then if a reaction occurs in the forward direction, what happens is that the number of particles changes, and you lose sort of the particles which you had on the left side. So you lose this vector alpha r, and then the particles on the right hand side, they are created. And the rate is given by some combinatorial number. So it depends on the rate in your equation. So the forward rate reaction r. And there's then a combinatorial factor which describes how likely it is in some sense that these particles actually meet so that the reaction can occur. So this is described by this product of factorials. So this is just a counting argument, very similar to what Mark actually showed yesterday. And then there's another parameter. So there's actually, you assume that these reactions take place in a given volume of size v. And then what you want if a reaction occurs is that these particles which you need for the reaction, that they actually are in the same units of your volume. So that means that you need to scale the thing by 1 over the volume times this alpha minus 1. So v is a parameter of your system denoting the volume. So and I'm using this vector notation all the time. So the norm of alpha is just the sum of the alpha i's. Okay, so this is in some sense, the probability that all of these particles are in the same unit volume of your space, so that the reaction can occur. Okay, and then there's the similar thing in the other direction. So if you have a backward direction, you get the analogous thing. So then you gain the alpha particles and you lose the beta particles. And then you have the backward rate. Well, and you get exactly the same thing, but now the roles of the alphas and the betas is exchanged. Okay. Yeah, so you see that this is a Markov chain model to describe these chemical reactions. Okay, what you can do then is, of course, you can look at the law of your Markov chain. So this evolves to an equation, which is just sort of the forward equation for this Markov chain, and this equation is called the chemical master equation. So to introduce notation, so let u of t. So this is a probability measure on my state space, which is sort of the lattice. So let it be the law of n. Then ut satisfies the usual forward equation, and this is called the chemical master equation. So this is just an infinite dimensional linear ODE. So let me give it a name. So u dot equals b of dt, where b is just an infinite matrix. Okay, so that's sort of the stochastic model that I would like to consider. And let me now introduce the deterministic model. And that's actually what appears in the exercise by Mark. So the deterministic model So then the observable is the concentration of each of your species. So this is now also a vector in R plus to the D. And this represents the concentration of the species. And now the model is that this concentration evolves according to a ordinary differential equation, deterministic equation. So CT evolves according to an equation which is sometimes called the reaction rate equation. Which looks as follows. So it's an ODE, nonlinear ODE. C dot equals minus R of C. This is shorthand notation. So what does it look like in components? So this is what Mark wrote. So Ci dot, so the time derivative is equal to the following. So you get a sum over all your reactions, 1 to R. And then you get some monomial terms. So there's the reaction rate, forward rate of reaction R, times the product of your concentrations, Cj T to the power alpha j R. So the idea being that well, no, let me not say anything. And okay, and then there's the reaction rate in the other direction. And then you get the beta j's. Okay, so this is just a system of ordinary differential equations with this polynomial right-hand side. Okay. Oh, and then there's something missing. There's the, of course, there's the change in your number of species. So you get the difference of this alpha minus beta. Okay. Okay. So this is an ordinary differential equation for the concentration. What you can do is, if you have an ODE, then you can actually lift it to the space of probability measures. So, for instance, suppose that you do not start with a deterministic concentration, but you start with a random concentration. So then you can look at the law of your concentration at time 0, and this law evolves then according to a PDE. So let rho t now be a probability measure on my continuous space, which represents the law of your concentration. Then rho t evolves according to PDE, which is called the Liouville equation. According to the Liouville equation, and this is just a transport equation in which sort of the vector field is given by the vector field which drives your differential equation. Yeah, so if you start with just a deterministic initial condition, then it's just the delta function. Yeah. So I consider yeah, so if you have stochastic initial data, then it will be an arbitrary measure, and then this measure evolves according to this equation. So this is the following transport equation. So dt rho equals the divergence of rho, so dt rho c, divergence of rho c. But of course, you're perfectly right. So there's no randomness in the equation, so the only randomness can come from the initial condition. And only in this case, sort of, this will be a non-trivial measure. In the sense that it will not be a Dirac.
Are you going to say something about the relation of the two models?
Right.
Yeah, I remember that the chemists would say, that this is insufficient in circumstances. This, basic kinetic law.
It's insufficient.
It's insufficient, yeah, because it doesn't take care of depletion. And, so if you look at cellular reactions, then this is just not.
Yeah. I mean, it's sort of the very simplified model in some sense. Yeah.
No, that's fine, but that would mean that we cannot do anything. But the point is that this is, there's a consensus that this has to do something to do with chemical reactions. It's been used in cellular chemistry, and it was found blatantly insufficient.
Okay.
But there are also lots of cases where it's perfectly okay.
Yeah, I guess
there's always with every model you have
in the brewery, I guess, or something like that.
Yeah, of course.
Yeah, so this is really sort of the very basic model which you would come up as a first approximation of.
Well, that one should be better.
That one is bad. Yeah, I mean, sort of. Yeah. But I'll show how these are related actually. Okay. So maybe let me draw a diagram. So in order to sort of, because we have now a bunch of different variables. So let me draw it here. So we have actually. So we started with this continuous time Markov chain. So we counted the number of particles. So this was a number in my lattice, which evolves according to this continuous time Markov chain. Then we lifted this to probability measures in some sense. So we considered this chemical master equation. So UT was in the space of probability measures on my lattice. And it evolves according to this chemical master equation. And then we had these deterministic models, so where we look at the concentration. So C of T, so this is just in my continuous space RD. It evolves to what I call the reaction rate equation. And then we lifted this also to probability measures. So this is sometimes a lift to probability measures. And we got this rho T probability measures on my continuous space. And it evolves according to this Liu-Bu equation. Right. Okay, then of course, a very natural question is what Marek was hinting at. So what's the relation between these models? And this is a very, very classical question, which has been settled by Tom Kurtz, I think in his PhD thesis actually. And what he showed is that if you look at this Markov chain, and you rescale it in the sense that you divide the number of particles by the volume, then the concentration at time, or the number of particles at time t, divided by the volume converges to this concentration. So the solutions to this Markov chain converge to solutions to this reaction rate equation. So that's what Tom Kurtz proved in the 70s. In a series of papers. Maybe let me write down something here. So Kurtz, he showed that if sort of the number of particles divided by the volume converges to C naught, then solutions to this continuous time Markov chain converges to CT. Where C is the solution to your reaction rate equation in probability. Okay, so what I would like to study during this lecture, I would like to look actually at these measure valued evolution equations and use a gradient flow approach. Of course, that's, I mean, in some sense you lose some of the information because you're not considered at this level, but I would like to make the point that still this gradient flow approach gives you some interesting information about the relation between these two models. And it gives you also some information about sort of related models which appear and sort of reasonable approximations. So reasonable continuous approximations to this discrete smart object.
I mean, that arrow where you're putting first, that's the equivalent to your gradient flow.
Well, I mean, in some sense, this is at the level of the process, really. So, and this is only at the level of your distribution. So, well, I think this is stronger at this level. Okay. So I would like to talk about gradient. Which left arrow? Well, it depends on what you need to know, but I mean, if you know the law of your random variable, then you don't know the random variable itself, right? So in this sense, there's more information at this level. Okay, so let me talk about gradient flows in this framework. Because there are actually many gradient flows around here. And one you already saw in the exercise by Mark, and that's actually not the one that I'm going to write down. No, I mean. So gradient flows in the setting. So if you want to speak about gradient flows, then we need some sort of reversibility condition. So we need to have what is called detailed balance. So there's one standing assumption which I will make in the rest of my talk. So I will assume that there exists a vector which I denote by the C star. So this is a vector of concentrations. And these are strictly positive, that's the assumption, such that detailed balance equations hold. And what does detailed balance mean here? It means the following. So it means that the forward rate times the product of these C's, so Cj star to the power alpha Jr. The notation is a bit heavy. Equals the same thing with the betas and the backward rate. Cj star to the beta Jr. And you want this to be true for all of your reactions from 1 to R. And we're going to give this a name, so this I denote by this kappa R star. Okay, what does this mean? So if you look at the equation which I just erased, I'm afraid. So if you look at the reaction rate equation, then you see that if on the right-hand side you have this sum of expressions of this type minus expressions of this type. So it means that it immediately shows you that C star is an equilibrium solution for your reaction rate equation. But it tells you a little bit more because it actually shows you this assumption that each of these reactions individually is in equilibrium. So it's a little bit stronger than just saying that it's an equilibrium solution. Okay, so we're going to assume that such a thing exists. And then actually there are a number of gradient flows which appear. So then actually this chemical master equation has a gradient flow structure. The reaction rate equation and also this Liouville equation all have gradient flow structures. Okay, so let me, I mean, I won't give you the details about them, but I'll write down at least some things about them. So this chemical master equation is just a forward equation for a Markov chain. And this condition actually implies that you have detailed balance for this Markov chain. So by what we saw in the first lecture, we can write down this gradient flow structure. So what it means is that I can write down my chemical master equation in the following way. So I can write my solution u dot as in the following form. So there's a symmetric matrix K of u, such that I can write the equation in this form. So the right-hand side is this gradient flow structure, where this driving functional E is the relative entropy. So E of u is the relative entropy of u with respect to some measure which I denote by WV, so it depends on the volume. And this measure is actually a Poisson measure, just like in Marek's talk before. And you can write it down explicitly. So this measure at the lattice point n, so the measure on this lattice, is given by some normalization e to the minus v times the norm of this c star times, and I'm using again this vector notation, so c star to the power n times v to the power n times n factorial, divided by n factorial. So this is a product of Poisson measures in which the intensity is given by this C star coming from this assumption. Okay. So this is just a gradient flow structure written in a sort of shorthand way, the same that we discussed in the first lecture of this series. Okay, then there's another gradient flow structure for this reaction rate equation. Yeah, so this is the relative entropy of U with respect to this measure. Right. Okay, then there's okay, so what I'm saying is that there exists a positive definite infinite matrix, which I denote by this curly K, such that you can write this equation in this way. So in some sense, this K is the inverse of your Riemannian metric. So it's just a shorthand notation for the gradient flow structure. Okay, then for the reaction rate equation, so there's a gradient flow structure, and this has been actually discovered by Mielke. So he showed that you can also write the equation for C in a similar form. So C dot equals minus another K times the derivative of my entropy. And now this entropy is now sort of the relative entropy with respect to this C star. So EC is the relative entropy with respect to C star. So this is a gradient flow structure for the ODE. And I can write down what the K is actually. So maybe let me do it. So again, this is a positive definite symmetric matrix. So I sum over all reactions. Then there's these constants appearing. Then there's the logarithmic mean, just as we saw for the Markov chains. So there's this theta function. And then there's sort of the quotients of C's. The logarithmic mean of some expression involving the concentrations. And then there's these alpha and betas, these reaction rates. And the product of them. Okay, so don't worry too much about the precise expression. So the point is just, for now, that there is a way in which you can write this equation as a gradient flow. The deriving function of this is this relative entropy, and there's an explicit expression for this, for the inverse of the metric.
I'm slightly confused about the relative entropy because C star is not a probability.
Yeah. Okay.
So you mean just the formal expression that you just write the sum over the coordinates of the C star log C over C star?
Right, exactly. Yeah.
So you normalize the case.
Okay.
So you should write it. That's not quite following.
Yeah, so let me write it down. So what is E of C is the sum of, say, this guy times H of Ci divided by Ci star. Right. And this H of T is T log T minus T plus 1. So this is actually important, the minus T plus 1, because you don't have probability measures. So usually you don't see it. But this is the precise expression. I was trying to sweep that under the rug, but you noticed. Okay, so this is a gradient flow structure. And there's actually then an induced gradient flow structure for the Liouville equation. So that's the third gradient flow structure which appears in that picture. So for Liouville, I can again write it in that form. So rho dot equals minus, and there's another k. So this time I use this sort of boldface times derivative of my energy E. So what is this E? This E is now an energy which involves sort of this previous E. So this boldface E of rho is just the integral of EC d rho C. So now you use this sort of entropy-like functional as an integrand in this expression. Okay, and this funny k you can also write down explicitly. So this k rho acting up on some function psi at C is minus the divergence of rho C times k, and now there's this again the k from the previous formula. So this k times the grad of psi. Okay. And if you look at this, then actually you recognize this also from Mark's talk. So this is actually the thing which you see in the Wasserstein gradient flow structure. The only additional feature is that there is this k appearing. So if this k would not be there, if it would be the identity, then it would be sort of the thing for Wasserstein gradient flows. So this is the same thing, but now there's sort of a non-trivial metric on the underlying space, which is sort of induced by this gradient flow structure. So the gradient flow for the ODE induces a Riemannian structure on your Euclidean space, and then you use that in the gradient flow formulation for this PDE as well. Okay. So that's a remark. So the induced some distance is the Wasserstein, so it's W2. With underlying Riemannian metric say the inverse of K. Okay, so these are the sort of the gradient flow structures which appear in that diagram. So now the question is, in some sense, how are these gradient flow structures related? So can we sort of pass to the limits from the gradient flow structure at the discrete level, so for the chemical mastery equation, to the gradient flow structure for the Liouville equation? Okay, so I would like to pass the limit in the gradient flow structure. So this gradient flow structure is determined by two things. So it's determined by the driving functional and by this operator K, which is sometimes called the Onsager operator. Okay, so passing to the limits. So let me first discuss the passing to the limit in this Onsager operator. And I won't say too much about that, so maybe I can use that space actually. So let me use again the notation that also Mark used with these psi and psi star operators. So I write psi star for the chemical mastery equation. So that's this functional, and in this case it's just a quadratic functional. So it's the inner product of psi with this funny K matrix. Where is it? So it's this curly K. K of u times psi. So that's the dual dissipation functional, which is quadratic. So this is for u probability measure on my lattice, and for functions psi on the lattice. And I didn't emphasize it in the notation, but remember that in this chemical mastery equation, the whole thing actually depends on the volume. So this K depends on this parameter V, which played a role. And that's the parameter that will go to infinity. Okay, and then there's the psi star for the Liouville equation. So rho and psi, so it's exactly the same thing, quadratic functional. And in this case, this is precisely this Wasserstein inner product, right? So if you use the definition of K, which I wrote down, then this is just 1/2 times the integral of grad psi times this K grad psi d rho. So this is for probability measures on my continuous space. and for functions psi on my continuous space. So functions for which that makes sense. Okay, and then what we can show, and it's not too hard actually, is to show that actually this functional, this psi star functional, converges to this one if you let phi tend to infinity. So sort of proposition. So that's something we looked at with Alex Mielke in a paper that we will finish very soon. So we show that that sort of this psi star for the CME converges in a suitable sense if you let the volume tend to infinity to the psi star for the Liouville equation. So in some sense, it's sort of consistent with Kort's results, and it tells you that also sometimes the metric for this gradient flow structure converges to so the one for the chemical mastery equation converges to the one for the Liouville equation. Okay. So in some sense, it's a little bit technical, but in some sense, it's a Riemann sum approximation. Yeah? So you have something on the lattice. So you can imagine that there were these discrete derivatives, which we saw in the first lecture. So in some sense, you can imagine that something like this will pop up. It's not completely obvious that where this k comes from, but it will appear in the calculation. Okay, so maybe I won't give you the details about that, but I would like to say something more about sort of the convergence of the driving functionals. And so of the relative entropy for the CME, and to show you how it converges to that functional over there. Okay, so let me pass to the limit for the relative entropy. So what I would like to show is that this, what was my notation? This the driving functional of my chemical master equation. So I will actually have to rescale it if I divide it by v. Then this will converge in a suitable sense to the driving functional for my Liouville equation, which is this E bar. Okay, and let me explain you heuristically why this is true. And this will also be a bit reminiscent of the arguments that also Mark was sketching in this discussion about entropy. Okay. So let me write down what this function actually is. So recall the definition. So 1 over v times that guy of u. So it's a relative entropy, so it consists of two parts. So there's the 1 over v. And then you get the sum over points in your lattice of un log un, sort of an entropy term. And because it's the relative entropy, a similar term where you divide by this reference measure. So you get minus 1 over v times the sum over n of un times log of the reference measure. And the reference measure, if you remember, it was this w. So this is this wv. Okay, so that's just the definition of this functional. So let's see what happens with each of those terms. So maybe let's give them a name. So this is maybe E1, depending on V of U, and this is E2. Okay, and so we look at the limit in which V tends to infinity, but at the same time we sort of rescale our lattice. So we study the limit where V tends to infinity, but we want to rescale our lattice such that if we look at at some lattice point n, it will also go to infinity, but in such a way that the ratio converges to ck. Okay, so now suppose that I have a measure on my continuous space, and I have a measure on my lattice, which is a good approximation. So suppose that I have a probability measure on my lattice, which approximates a probability measure rho on the continuum. And so this is just a heuristic argument, so I'm not going to make anything precise. Okay, then if you look at this first functional, so this guy, the first term, well, you see easily that this is roughly equal. So this guy of rho, no, I mean of u, this is roughly the same as 1 over v times the integral of rho log rho. Again, it's some sort of a Riemann sum. And there's actually sort of a correction term. This doesn't really matter, so there's the dimension times log v over v. But this is just a constant, so we don't really care about it. Well, and then you see that this is something of order 1, and we divide it by the volume, so this term will disappear in the limit. So the first term converges to 0 as v tends to infinity. Yeah, because this sum is something of order 1, and we divide by the volume. So the thing which will survive will come from the second term. Okay, so let's look at the second term. And in particular, let's look at sort of this expression, so 1 over v times the log of this w. So minus 1 over v times the log of w. Well, we have this completely explicit formula for this w, so we can just write out what it is. So remember, it was given over. So this was this Poisson measure, which was given over there. So if we take the log of it, we actually get something which looks quite nice. So you see that it will be equal to the sum of I from 1 to d. Then you get minus ni over v times the log of v times ci star plus the log of ni factorial divided by the volume plus ci star. So that's just using the explicit formula for the invariant measure that we had over there. Okay, so this is a little bit reminiscent of what Mark was discussing yesterday. So of course, what we would like to do is we would like to use Stirling's formula to compute this guy. So using Stirling, so we use that sort of the log n factorial equals n log n minus n plus some remainder we don't care about. And what you find if you replace this log of n factorial by this expression, you find that this is exactly equal to this energy functional E, which is still over there, of n divided by v. So you just use Stirling, and then you see what you get, and it's exactly precisely equal to this. Okay, then it's of course almost done, because then you see that sort of this discrete functional, so 1 over v times this e. So this is approximately equal to this, well, so this will now be a Riemann sum, right? So there's this un times this guy. So we have this e of n divided by v times un. And because un is a good approximation of this continuous measure rho, so this is roughly the same as EC d rho, which is the energy at the continuous level. Okay, so in some sense, what happened here is that this term is just small because we divided by something of order 1 divided by the volume. And here we used this Stirling's formula to compute this expression, and we see that something survives in the limit, and we can use Riemann sum approximation to pass to the limit. Okay, so this shows at least heuristically that the driving functional for the discrete system converges to the driving functional for your continuous system. So what this in some sense shows is that because we have convergence of these psi star functionals, we have convergence of the driving energies. So it shows that the associated gradient flow at the discrete level should be a good approximation to the gradient flow at the continuous level. So this shows heuristically that sort of the Liouville equation is a good approximation to the CME for large V. Okay, but I mean, what this suggests is maybe we can do actually a little bit better. So this Liouville equation is a good approximation, but maybe we can find a better approximation using this heuristic. Because I mean, the Liouville equation does not take into account the volume of your system, but it would be nice to have an approximation of your chemical master equation using a continuous model, which still takes into account the volume of your system. So the question is, can we find a better approximation? Okay. Well, and so this gradient flow approach suggests a natural way to come up with better candidates. Right, because we can sort of have a closer look about this convergence of these driving functionals, for instance. So first look is you can look at this functional, but now we just threw away these terms, but you can actually still keep it and look at the gradient flow equation in which you still take this term into account. So sort of a first guess would be that you actually look at this functional, but you keep this term, and you look at the gradient flow equation for that thing. So consider the following functional. So a functional which I know by again this boldface E tilde, which now depends still on the volume. And now I take the same thing which I had before, so the same energy functional for the Liouville equation. But I would like to take into account also this first term. So if we do that, sort of the natural thing is that I get 1 over the volume times the entropy, times the integral of rho log rho. Okay, and then the natural thing to do is that you look actually at the gradient flow of this functional. So what you obtain then is not just this Liouville equation, which has only a transport term, but you also obtain a diffusion term, which comes from this entropy. So this leads to an associated gradient flow equation. Which will be something like this. So dt rho equals minus this k of rho times d of this energy of rho. So this will be now a Fokker-Planck equation with a drift term as before and a diffusion term of the order of 1 over v. Okay, so that's a better approximation in some sense because we took into account also this 1 over v term. But actually there's something even better that we can do. Because now we only took into account this term, but we can also look again at this term and also have a look at the terms that we threw away, because here we made the approximation using Stirling's formula. So let me give you a better approximation. And so this approximation really comes very naturally from this gradient flow approach, and I think that is one of the reasons why it is interesting to look at this from this gradient flow perspective. So a better approximation is obtained if we use sort of a more careful version of this Stirling's formula. So you use Stirling in the following form. So you use now this log of n factorial is approximately equal to n log n minus n, but you keep some extra terms. So the next order term will be 1/2 times the log of some junk, which looks like this. And then if you take into account also these lower order terms, you find the following. So if you do exactly this computation, you find that this 1 over v times the log of this measure, this will be approximately equal to the following. So the same thing what we had before, so the energy of n divided by v. But now there's a correction term, which is 1 over v times some function depending on v, evaluated n over v. Well, where g is just some function which you can compute, and it comes from this lower order correction term. I can write it down explicitly, but it doesn't really matter so much what is the precise formula. So gv of c is the sum 1/2 of log 2 pi times v of ci plus 1 over 6. That's just what you get if you apply this more refined version of Stirling. Okay. Well, and then the natural thing is to take this into account and look at the gradient flow of this functional. So what you obtain is the following. So let me continue just below here. So this leads to the sort of the functional that we obtain using this approximation. Now looks like this. So denoted by this E of V of rho. So to first, I mean, sort of the main term is again the same thing which we had before. then there's this sort of this entropy term, so 1 over v integral of rho log rho. And then there's another drift term involving this function g. So now we can look at the gradient flow of this functional, and the new equation, what you get is the following. So this will begin the gradient flow of this guy. So rho dot equals minus k of rho times dE of rho. And if you write this as a PDE, what you get is the following. So you get dt rho consists of the following terms. So it's the divergence. The first order term will be the thing from the Liu view, as we had before. Then there's the diffusion term. So there's a 1 over v times this diffusion matrix times the grad of rho. And then we get a correction term, which is a drift term in my equation. It will look like rho times some vector field A. Well, and this A is just, some explicit vector field which comes from this function G. So where A, depending on V of C, is this matrix K applied to something which comes from this term. So the precise formula is not very important, but it looks like this. Yes, that's right. So again, thanks. Right, so these are the sort of the K's which came from the reaction rate equation from the ODE. Yeah. Okay, so the point that I'm trying to make here is that sort of this gradient flow formulation gives you a very natural sort of way to end up with good approximations to this chemical master equation, just by looking sort of at the asymptotic behavior of these driving functionals. And I think that's not something which you would easily see just by looking at the models directly, or looking at the equations which you obtain. But this is really something which pops out very naturally from the gradient flow structure. No, in some sense this is formal. So we don't have any convergence results actually for the PDEs. That's something that you would like to do. So we have sort of rigorous convergence results for the functional and for the dual dissipation functional. So that's rigorous, but we don't have any convergence result actually for this equation, which compares it to the well, for this, I'm sure that would not be so hard. But we don't, yeah, so it will be interesting to compare sort of quantitatively how much does this actually improve your approximation. And we don't have any rigorous result on that yet. Right, so that's a very good point. Yeah. So so now I only included sort of the lower order terms for the driving functional, but it would be very natural also to take into account the sort of the next order terms for the K. Yeah. It's also not included here, but that would give you an even better approximation, I would suppose. That would be a very natural thing to do. We didn't do it yet. Okay, I think I